Hi there, welcome back to Severe Weather. We're going to be talking about multicells and MCSs. So, something that might be a little bit confusing when you're just starting to learn these terms. MCS doesn't stand for multicell storm, even though you might think that seems like it could be, but it actually stands for mesoscale convective system, which are two different concepts that we're going to talk about in this video. We're going to start out with talking about multi-cell storms. We have already talked about ordinary single cell storms before, but what's the difference for multi-cell? Well, it's what it sounds like. It's a grouping of convective storms, so there are multiple cells. Now, these different cells are likely going to be in different stages of the storm life cycle, and the new storms can form due to the gust front forcing on the low level inflow side of the storm. The gust front is going to be the boundary on the edge of the storm, and it's characterized by a change in temperature and wind direction speed. It almost is like a miniature front, hence the name that it has. For multi-cell storms, they need what's called a cold pool, and that is going to be supplied from the downdraft. Now, the we're going to talk a little bit more about cold pools a little bit later, but they are going to be important for storm organization, although the strength of it is not really a parameter that we'll see later. It doesn't necessarily mean the stronger the cold pool, um, the stronger this storm will be, or the more progressive it could get. But we'll talk more about that in a second. Now, there is inflow and outflow for the storm, and the inflow provides fuel, which is warm, moist air. If it gets cut off, it can get cut off by the outflow sometimes, and then the storm will die. Now, sometimes from a cold pool being too strong, that can happen. Um, and I'm going to actually go to this slide just for a second to see that for a little bit. So you can have a weak or a strong cold pool, and you can see that the difference between these two images is the way that the storm is organized. So it's different. You have cell A here, then cell B, cell C, cell D, like that. Here it is in a different direction. But overall, it's a slightly different organization that we have. But once again, we don't want the cold pool to be too strong or too weak. Kind of a middle ground is going to be more what it is, but it's kind of an abstract thing to really calculate. But it is an important part of multi-cell storms. The progression of multi-cell storms is similar to ordinary thunderstorm life cycle. We have the towering cumulus stage, mature stage, and dissipating stage, and we talked about that already in a different video. Um, there are different types of multi-cell storms. One is a multi-cell cluster, which is a cluster of cells that generally lack orientation. So they're kind of random a little bit, just kind of scattered, sort of. The cells are in different stages of life cycle, um, and there's moderate instability and typically weak shear. You can also have a multi-cell line, which is what it sounds like. It's a line of storms that progress on the same axis. So whereas the cluster was kind of random, the line is going to be on the same axis. Um, Still in this case, the cells are going to be in a different stage of the life cycle. Um, Typically, it's going to be too weak of boundaries for it to be a squall line, and too weak of shear or instability for it to be considered supercell. And we'll talk more about that later in the video. So I already went over that. Um, Now we'll talk about something called MCSs, which are mesoscale convective systems. Mesoscale is telling us that it's going to be something that's large. So it's really just large convective systems. They are convective systems that are specifically larger than supercells, and they include squall lines and derechos. In the next video, we'll talk a lot more about derechos specifically. But the thing about MCSs is that they have a common cold pool, and the key is low-level forcing. So squall line. A squall line is a I said that typically multicell line can be too weak of boundaries to be a squall line, but sometimes the multicell storms can end up being a squall line, and they are in a linear pattern on a linear boundary, which is typically a cold front. The propagation of the cold pool determines the thunderstorm development and longevity. And the leading edge is the gust front or outflow boundary, which we talked a little bit about before. And there is going to be strong convergence in the low levels. A cold pool is generated by stratiform precipitation. The stratiform precipitation of a storm is going to be the kind of lighter, more meh, that's not really a scientific word, but not the heavier, stronger, more dramatic precipitation. Stratiform is the more light precipitation. And we will learn later that where that stratiform precipitation is in relation to the main part of the storm is going to help determine the strength and longevity of that also. But um, if there's more vertical tilt for the squall line, increased severity of winds. And sometimes the squall lines can have supercells within them. Characteristics of squall lines. Um, the shear vector boundary orientation is going to be strong and deep. The boundary forcing is going to typically be weaker. The amount of sin is high and low-level convergence is parallel. For storms that are just discrete, it is the opposite for all these situations. What are the things that we need for squall lines? We need low-level moisture. We also need mid-level flow of 25 knots or more. You can look at the 500 millibar level of SQT to help you determine this. And you also need strong forcing, which will typically be the cold front. You can sometimes have what's called undulations in a squall line, which is kind of a wavy shape that's caused by uneven flow and increased speed of the gust front. Let me move my camera. Hopefully it actually moves. Sometimes it doesn't. But we're going to talk about something now called loops, which are stands for long or line echo wave patterns. This is includes multiple bows, and the bowing in storms is kind of a curvature if you want to think of it like that. And in some cases, it will kind of have a like a comma shape. And loops include undulations, which we talked about. It's kind of like waviness. There's increased severe. These will increase the severe threat, and they're caused as air moves from the mid levels to the surface. And the process that this is stratiform rain falls. The cool air is entrained. There's evaporation taking place, increased downdraft winds, and Rij to the surface. We are going to talk about what the Rij is in a second. So the cold pool of a squall line, it controls the speed of the squall line, and new cells are going to be formed on the leading edge of it. Rij of squall line. So Rij stands for rear inflow jet. It is a narrow band of fast-moving air on the backside of an MCS, which can cause a bow. A rear inflow jet is caused by converging winds in the mid-levels. You can see that with the rear inflow jet and the converging winds, there ends up being a storm scale low in the mid-levels. But at the surface, there's high and diverging winds. Rear inflow jet strength. If it is stronger, there's increased instability, greater transport occurring, and more damaging winds. So, what is the reason that the rear inflow jet is going to create a storm scale low in the mid levels? Well, air is going to be forced up, and once it is, it condenses. Condensation is a warming process, if you remember, back to our earlier videos. Um, and a low ends up being created from the warm, moist air rising. Winds are diverging at the surface, like I said, and there's a high, and they're converging aloft, which is where there's the low. With the dew point depression, there's more evaporation, which strengthens the cold pool, because evaporation is a cooling process. Where there is a bowing segment in the radar, there are oftentimes stronger winds at the surface. Now, you can identify the direction of wind flow by looking at uh, radar aspects, and in this case, there is a certain um, viewing aspect where you can see red and green to help indicate inbound or outbound. Um, Now, what does this mean? So the X on this slide is representing where our station is. And red, areas of red, now this is just squares, but it would really be a complete filled in area, like obviously. But this is just for the example. But red indicates that there is a detection that wind is going flowing away from the station. Green is towards. So if we had a situation like this, once again, it really would be all filled in. But if we just had an abstract example like this, we can see how the winds would flow. Um, Anywhere where it's red, you know that the wind is away from the station. Anywhere where it's green, it's flowing towards. So in a situation like this, um, for this top and bottom, as you can see, there's two different directions with respect to the station. It's going away and then towards. So for both these situations, we might expect that there is some kind of circular movement going when you have um, basically they are both aligned like that by the X. They're not in front of each other, they're side by side, if you see. Like for the ones that are to the left and right, they're blocking the other one. But for the top and bottom one, they're side by side. And you can see by this that this is counterclockwise, or sorry, clockwise for this top one and counterclockwise for the bottom one. Therefore, this is anticyclonic, this is cyclonic, and you can see that there's convergence occurring and divergence. So all these things you can detect just by seeing the red and green. So that's the point of this slide, just to tell you that. Now let's talk about some uh, types of squall lines. There are three different types to know, and it says MCS subtypes because squall lines are a type of MCS, so this can be applicable to other MCSs as well, but it is determined by the upper level relative winds. Now, this is what I was talking about before. Where the stratiform precipitation is helps us to know the strength of the storm. So the first one we'll talk about is trailing stratiform, this bottom image right here that says TS. Now, what's the deal? What does this mean? Well, we have the strong cold pool behind the storm and stratiform precipitation behind the storm, trailing behind it. So, also, that's where the anvil is. So you can see this is the anvil that's sticking out. And the storm, you can see, is headed in this direction. Now, the cold pool is enhanced, and there is more severe winds in this case. Um, for leading stratiform, it's this top one. Well, this time, stratiform precipitation is ahead, and this actually results in a weaker cold pool. And it's typically slower moving, and this is going to cause a weaker winds for this one. Parallel is if the anvil is behind and ahead. The stratiform precipitation is ahead and behind, kind of like evenly like that. It's not as common for that to be the case. Um, so the anvil formation, if we have the storm moving faster than the winds, the anvil ends up being behind, and the stratiform precipitation is behind, which is the trailing stratiform case. If the storm moves slower than the winds that are blowing, then the anvil ends up ahead of the storm, and the stratiform precipitation is ahead of the storm, which was our leading stratiform situation, which has weaker cold pool and weaker winds. So basically, our type of squall line can be determined by how fast is the storm moving in relation to the upper level winds that there are. Now let's talk about how the Coriolis force um, affects our MCSs. So just as a review for if you don't remember what this is, it is a force that has a di results in a deflection of winds. Why? It's caused by the Earth's rotation. And in the northern hemisphere, which is where we are, it results in a deflection to the right. So there's counterclockwise, or apologies, um, clockwise flow for high pressure systems in the northern hemisphere, counterclockwise for lows. And the further you get from the equator, the Coriolis force is stronger because it is maximum at the poles and zero at the equator. Now, how will the Coriolis force affect MCSs? Well, it's actually going to result in a partial rotation of the MCS. The northern part of the MCS is going to be more affected by that because, once again, Coriolis force is stronger the more north you go in the northern hemisphere, of course. Um, we can have what's called line end vorticities because of this. It's rotations on the end of the MCS. And on the northern end, we have cyclonic or counterclockwise flow. On the southern end, which is not as strong, anticyclonic or clockwise flow. Bow echoes. We already talked about this slightly, but let's go into a little bit more detail about what they are. It is an indication of a rear inflow jet making its way to the surface. It is a bow-shaped part of a convective cell. It provides large areas of damaging winds. The size of bow echoes is highly variable. It could be 10 to 65 miles long. There is a hail threat associated with bow echoes in the early stages of MCSs because a long updraft is needed for hail, and we have that in the early stages. Tornado threats, there can be possibility of small tornadoes in the early stages of MCS in these bow echo regions. How do these bow echoes affect our storm? Well, it's going to cause it to be more comma shaped. So see this image. The bow happens, and we do know once again that there are line in vorticities, so you can see there's slight rotation on the ends of the storm. But there is more in the north, once again, because Coriolis is stronger. So that's why it curves more for the top part of it, resulting in a comma shape. Mark signature. So we'll talk about something called Mark signature now. Um, it stands for mid-altitude radial convergence. It is an area of convergence within the mid levels of a thunderstorm. That's the main thing to know about it. Identifying straight line and downburst winds. How can you identify these? Well, you can look for the loops that we talked about, look for weak echo channels of the rear inflow jet, and convergence winds aloft and divergent winds at the surface. Those are some of the features that we talked about earlier. Well, that's going to be it on this video. Thank you for watching.